Okay, excellent. So welcome to the last talk of the workshop, but definitely not least. And our speaker is Raghu Meka from UCLA.
Hello, everybody. Thanks for the invitation to speak at the workshop. Today I'll talk about Gaussian graphical models and learning Gaussian graphical models with few samples. This will be similar to Ankur's and Mark's talk. The main difference would be that we'll be dealing with continuous random variables instead of discrete random variables. And this is based on joint work with John Kellner, Freddie Kohler, and Ankur. So here's kind of the rough outline of the talk. First, I'll talk about what the Gaussian graphical models, or GGMs, are, the motivation behind studying them, what the central question is. Then I'll describe the special models that we'll study and where we actually solve the problem with the simple algorithm, which is summarized in this small bullet point here. And then I'll say a few words about the analysis. I won't be able to go deep into it, but I'll probably should be able to highlight the main ingredients. So let's get started. So what is a GGM, or Gaussian graphical model? It's essentially just a multivariate Gaussian distribution. Let's say X here, which has a covariance matrix sigma. So throughout, we'll think of the ambient dimension as P, the number of variables. And here, if you're curious, this is the exact PDF for what a multivariate Gaussian distribution with covariance matrix sigma looks like. So usually when we think of Gaussians, we parameterize them by the covariance matrix. But in the graphical models literature and today, we'll instead mainly focus on a related matrix, which is the precision matrix, theta, defined as the inverse of the covariance matrix. So why look at the precision matrix? And the reason we'll look at it goes back to this fundamental fact found by Dempster in '72, who showed that the precision matrix encodes certain additional information about the distribution. In particular, it encodes the conditional independent structure of the distribution. So what do we mean by this? So let's say you have the precision matrix theta, which is defined as sigma inverse. And given the matrix, we are working backwards now in some sense. I define a graph whose edges are given by the support of the entries in theta. So if an entry ij is non-zero in theta, then I add an edge between the vertex I and j. So the number of vertices is the number of variables p. Then the Gaussian distribution satisfies the Markov property with respect to this dependency graph G. And this should be familiar from Ankur's and Mark's talk, where they also talked about how this same structure appears in Ising model. And the same thing happens here for GGMs as well. So if an entry ij is 0 in the precision matrix, theta, then the corresponding variables are independent, conditioned on, let's say, the neighbors of the vertex I. They're actually independent condition on any separating set, but we can just focus on the neighbors of I. So for instance, in this toy example, the variables x1 and x3 could be correlated with each other. But once I condition on x2 and x5, they become independent. And this is the information that is encoded by the precision matrix as opposed to the covariance matrix of the Gaussian distribution. And so far, I mean, we've just, it seems like we just changed how we describe a Gaussian distribution. Instead of looking at sigma, I'm looking at sigma inverse. But the main non-triviality of looking at the precision matrix comes when I characterize the complexity of GGMs by limiting what the dependency graph can look like. So throughout this talk, we'll focus on GGMs, which are simple in the sense that the maximum degree of the dependency graph is at most d, which we'll think of as being much smaller than the dimension p. And this is the assumption that makes the formalism of GGMs non-trivial and useful. So why GGMs? First, it's a very useful model for modeling statistical relations, especially between continuous variables. We saw what we can do with discrete variables in the previous two talks. I won't go into the history and the known literature in those works, but I'll mainly focus on the continuous setting today. And it also is useful in many applications in supervised and semi-supervised learning, especially in the natural sciences. It's used to model gene regulatory networks, brain connection networks from fMRI. And I recently found out there's surprising applications various works in applied sciences which use GGM software. So let's look at an example to make this model very concrete and why it's kind of interesting. So this is a model that I'll call the random walk model. So here, I first generate Z1 to Zp, which are IID standard Gaussians. And each xi is just the sum of all the z's up to I. So xi is xi minus 1 plus zi. So it's just a prefix sums. Now, what does the covariance matrix of this distribution look like? It kind of looks nice. It's this nice, big, dense matrix, which has this nice structure. But how about the precision matrix? The precision matrix turns out is actually very simple. It's just this sort of tri-diagonal matrix. It has only 3 non-zero entries for each row or column. Now, if I look at the dependency graph that you get out of this, it's just the path. And this makes sense because if you go back to our description of our generated description of the model, then conditioned on xi minus 1, xi is independent of everything that appears before it, and so forth. And so it makes sense that the dependency graph is a path. So we're interested in 2 main problems in the context of learning sparse GGM. That is structured learning, that is, given samples from the GGM, can I learn the dependency graph of the GGM? And parameter learning, where along with structured learning, I'd also like to learn, let's say, estimate the precision matrix theta or some other properties of the GGM. So more concretely, I'm given samples x1 through xn from a GGM, and our goal is to output the dependency graph of the GGM. So n will denote the number of samples, p is the dimension. So you want to go from just the samples to the dependency graph. And the challenge in many applications, as we saw in Ankur and Mark's talks, was that the number of samples that you actually have is much less than the dimension p. So unlike the discrete models, at least here, it's almost trivial to estimate the model when you have linear in dimension many samples. If you have O of p samples, you can just estimate the covariance matrix with remarkable precision, and hence also get the precision matrix with a very good accuracy. But the main challenge here is that the number of samples you have is much less than the dimension, and you still like to do something or learn something about the distribution. And this is possible because we have this assumption that the dependency graph is sparse. Each vertex has at most d edges. So here's our challenge question again. We have n samples where we're thinking of n as much less than p. The degree of the GGM is much less than p, and we'd like to learn the dependency graph. So we should think of achieving n, the number of samples, being logarithmic in p. Okay. And learning the dependency graph is the core of the problem, because once I know the dependency graph, I can learn the parameters or estimate the parameters by reducing into d by d subproblems instead of working in this big p-dimensional space. So believe me if I say that learning the dependency graph is kind of the main bottleneck in many inference and learning questions afterward. And ideally, we'd like simple algorithms with provable guarantees. Okay, so let's look at an example of what the problem might look like. This is unknown order random walk. So suppose there's some hidden permutation pi, and I have the same model as before, but the prefix sums are now computed according to the permutation pi. So you have Z1 to Zp, which are IID standard Gaussian, and x pi of I is x pi of I minus 1 plus Zi. What does the covariance matrix look like? This is something I generated using a random permutation. It looks something not so nice, but still very dense. And how about the precision matrix? It's also some jumbled version of the older matrix, and the dependency graph is still a path. And the learning problem for us is I give you the samples. I'll give you samples from X, and our goal is to find the hidden permutation. How many samples do I need to uncover the hidden permutation? And this is just a toy version of the problem to have a concrete example in mind. And going back to our problem, there are several popular software packages that people use, such as Glasso, Climb, and A-Climb for GGMs, for learning GGMs. And let me say a little bit about these results. So Glasso was introduced by Friedman, Husty, and Tibshirani in 2008, and they showed that the algorithm can learn GGM. They and subsequent works showed that the algorithm can learn GGMs with sample complexity that is d squared times log p. It's remarkable that the sample complexity is only logarithmic in the dimension p and polynomial in the degree d. However, this relied on assuming that the precision matrix was incoherent. I won't define what incoherent means, but it's kind of a condition saying that large submatrices or d by d submatrices of your precision matrix are very well conditioned. And just to contrast with the previous two talks, we could not hope to get O of d log p dependence for discrete models, but for Gaussians, you can actually hope to get d log p style dependence. And this incoherence assumption is actually a strong assumption in practice, and it is violated by even simple models such as random walk model that we saw. It's not incoherent. If you use the existing guarantees for Glasso, you get sample complexity that grows linearly with the dimension, which is not saying much about the problem at all. And similarly for Klein, this is a nice paper due to Sai, Liu, and Luo, who showed that you can learn GGM, the sample complexity, again, that is logarithmic in the dimension, but there is some polynomial dependence on the ratio of the entries in the covariance matrix to that of the precision matrix. And once again, this is kind of a conditional, this is kind of an assumption on the condition number of the matrix in some different norm, of the precision matrix in some different norm. And this is also violated by the random walk example. If you go back to the example, this ratio actually is more like P. So the bounds here do not go beyond what you'd get from standard Gaussians. Okay, so in summary, the known results for these problems assume you have some kind of well-conditioned precision matrix. And the main question is, can we go beyond this? And there are several reasons to do this. One is this well-conditioned assumption is kind of brittle. Scaling variables in some nice ways violates these assumptions, which is not a good thing for most theoretical results. And also it's violated by simple models, such as a random walk model that we saw. And it's not just that the analysis of these algorithms fails to capture the best bounds, but also the algorithms themselves do not perform well under the simple models, as we'll see later. So before going ahead, let's ask ourselves what is actually possible for this model information theoretically. And here is very nice work of Nisra, Gouffre, and Loka, which actually drew us to this problem, gives an almost complete answer. So to describe that, I need to first talk about a fundamental parameter that will show for the rest of the talk that I'll just call pairwise correlation. And it is defined as follows. You have your precision matrix theta, and for every entry ij that is non-zero, you look at the corresponding 2 by 2 matrix, theta ii, theta ij, theta ij, theta jj, and you look at the ratio of how big the off-diagonal entry is relative to the diagonal entries. Formally, you define kappa of theta as the minimum or non-zero entries of the ratio of the off-diagonal to the square root of the product of the diagonals. Intuitively, it measures the signal in the 2 by 2 submatrices of the precision matrix, kind of measures the edge interaction of the precision matrix and of the GGM and the dependency graph. And critically, it's a number that only depends on 2 by 2 submatrices and not on the whole matrix, which makes a big difference in various assumptions. And what they showed is that the dependency graph of any GGM with degree d is identifiable with roughly d log p by kappa squared samples. Okay. And this is very clear, very nice, because it's saying your recoverability only depends on this 2 by 2 submatrices, and intuitively some dependence on kappa is necessary. Because if you think of the off-diagonal entry as being really close to 0, you should not be able to detect it with few samples. And for example, if you go back to the random walk model and you do some calculations, you'll notice that the kappa, the pairwise correlation parameter there, was actually half. Okay. And to complement this, Wang, Wainwright, and Ramachandran, actually even before the work of Mr. Rufer and Loco, showed that for most GGMs, even for the special cases that we'll look at later, the number of samples that you need has to be at least log p by kappa squared. So the upper bound is off from the lower bound by a factor of b. So this seems great. However, there's one catch with the work of MVL, which is that the runtime of the algorithm scales as p to the O of t. So the runtime is polynomial time if you think of the degree as being constant. But if you think of even degree growing slowly, it becomes quite problematic. And the question that we'll address, and the main question is, can we do better? And again, this is kind of the same sort of runtime bottleneck that we are trying to avoid in Ankur stock as well as in Mark stock, where achieving p to the O of t was kind of possible, but we'd like to go beyond that. So the central question now is whether I can learn the dependency graph of a GGM with roughly d log p or kappa squared samples and runtime that is a fixed polynomial in p. So I don't want the exponent in p to grow with the degree d, or even, can I even get p to the little o of d sample complexity? And the main results of this work are that you can indeed do this for a large class of, for various special classes of models that I'll talk about in a little bit: attractive, symmetric, diagonally dominant, and more generally walk-summable matrices. And on top of that, we'll actually show that there's a very simple greedy algorithm, much like the one that we saw in Ankur stock, that solves these special cases, which can actually be pretty ill-conditioned. And in addition, also recovers the same guarantees that you could achieve with Glasso or Klein. Okay, so that's kind of the summary of the first part of the talk, where I talked about what GGMs are, why we study them, and the main problem that we are trying to study. Let me now move on to talking about the special models that we'll look at and what the simple algorithm that I alluded to is. So the first class of models that we'll look at are attractive GGMs, or antiferromagnetic GGMs. I keep getting confused between ferromagnetic and antiferromagnetic. So a model or a distribution, a Gaussian distribution for us, is attractive if all covariances are non-negative. Equivalently, if you look at the precision matrix, you want all the off diagonals of the precision matrix to be non-positive. This is a little bit, this is kind of the opposite of what Ankur talked about, where the interaction coefficients had to be positive. Here, you're assuming that the interaction coefficients are actually negative. Okay. So there are many special cases of attractive GGMs that are studied in machine learning, especially such as Gaussian free fields. These arise in many applications via Gaussian process and supervised and semi-supervised learning. For instance, the random walk model that we talked about, or that we looked at before, is an attractive GGM. As you can see, all the off-diagonal entries are non-positive. And even in these attractive GGMs, the resulting precision matrix, even if it has small degree, can be ill-conditioned. For instance, for the random walk model, as long as if the underlying graph has long paths, you end up with ill-conditioned precision matrices. All right. So there are no efficient algorithms that efficient, again, meaning that the runtime is a fixed polynomial in P, algorithms that achieve logarithmic sample complexity even for attractive GGMs. And the first main result we have is that we can in fact do this. And we can do this with runtime that is d log p or kappa squared and quadratic runtime. So the number of samples, is d log p or kappa squared, and the runtime is quadratic. And this we'll do by the greedy prune algorithm that I'll talk about in a few more minutes. Okay, and just to complement this, the lower bound of Wang, Wainwright, and Ramachandran actually applies even to attractive GGMs. So to learn attractive GGMs, you do need log P or kappa squared samples. And what this result is saying is that you can get d log P or kappa squared samples. If you can get that many samples, then you can achieve efficient recovery. All right, so the second more general class of models that we'll look at are walk-summable Gaussian graphical models. So this is a bit of an algebraic condition and says the following. A precision matrix, theta, is walk-summable if the following holds. You start with your precision matrix, and you now look at a new matrix where you make all the off-diagonal entries negative. So you replace each entry theta ij with the negative of the absolute value of theta ij. So by definition of Gaussian distribution, the original precision matrix has to be positive semi-definite. And what we need for the matrix to be walk-summable is that this transformation preserve positive semi-definiteness. So when I make all the off-diagonal entries negative, you want the matrix to still be positive semi-definite. And when that holds, you call it walk-summable. The reason for the terminology walk-summability comes from motivations in statistical physics. And this was introduced by Mariotto, Johnson, and Milski in 2006. And it generalizes many other special classes of Gaussian distributions that are studied in machine learning and statistical physics literature. For example, attractive models are clearly walk-summable because all the off-diagonal entries were assumed to be negative to begin with. So the transformation does nothing. And there's something called pairwise normalizable models, non-frustrated models, and symmetric diagonally dominant matrices that we'll talk about later. So I won't go into elaborating on what all these special classes are, except for SDD ones that I'll mention a little bit later. Okay. So for walk-summable models, learning walk-summable GGMs was also studied before, especially in the work of IMA Anandkumar et al. And the best result here is due to their work, and which has some additional constraints, but which were removed in the more general result of Mr. Gouffre and Loco. That you can learn walk-summable GGMs with runtime that is P to the O of D and logarithmic sample complexity. This is the best we know for general models anyway. And our main result is that you can actually get logarithmic sample complexity and quadratic runtime. So that is an efficient algorithm that learns walk-summable GGMs with d squared log p or kappa to the 6 samples. So the dependence on d and kappa kind of degraded a little bit, but it's still not too far. It's still only polynomial. And we have a different algorithm that we call hybrid MD or hybrid lasso algorithm, which combines our greedy approach with the more traditional lasso-based, regression-based approach, which achieves a slightly better sample complexity of d log p or kappa to the 4. All right, so now I've stated what our results achieve, and let me now describe the algorithm that does this. The algorithm is actually very simple, and we kind of already saw it in Ankur's talk, but here we'll be using a different sort of potential function. So just to recall, we have input is samples from a sparse GGMS, and our goal is to compute the dependency graph of the distribution. So the algorithm greedy prone has 3 basic steps. In the first step, you try to recover the neighborhood of each vertex in parallel. So just forget that you're dealing with n vertices. You just focus on one vertex and try to recover its neighborhood. And in the first phase, once you fix the vertex, let's say vertex 1, you try to grow a candidate neighborhood set for this vertex. And in the second phase, you prune out these vertices to end up with your final candidate neighborhood. So what do you do in phase 1, where you try to grow a neighborhood? So we fix the vertex 1, and we're trying to learn the neighborhood of vertex 1. So this is a greedy growing strategy where you start with the empty set, and in each step you add one vertex using a simple greedy rule. And the greedy rule that we follow is the following. In each round, you add the vertex that gives you the maximum bang per buck in terms of explaining the variance of x1. So in other words, given that you added, you've computed a set S, you find the set vertex j not in S, that minimizes the conditional variance of x1 given x variables in S union J. You don't have access to the exact number for what this conditional variance is, but you can get an estimate for that using standard estimates from such as ordinary least squares regression and so forth. So let's push this issue of working only with estimates under the rug and focus only on what happens if you have this conditional variance for now. So that's the intuition. And if you're familiar with the compressed sensing literature, this algorithm is actually equivalent to what is known as orthogonal matching pursuit algorithm for sparse linear regression. I mean, if you're not familiar, then forget this. But if you are, then I think it's a very good sort of connection to keep in mind. And yeah, so but for trying to understand what the algorithm does, it makes sense to keep the greedy approach as opposed to thinking of it as orthogonal matching pursuit. Okay, so that's phase one. What is phase two? So now you've constructed a candidate neighborhood. And the problem is that you might have some false positives in the sense that you might have added some neighbors, some vertices which are not actually neighbors, but you already added to a set S. And now you just prune them out using a simple rule, which is if dropping a vertex does not hurt you too much, you just drop it. So for each vertex in your set S, you do the following. Compute the conditional variance of x1 after dropping that vertex. If the conditional variance is not too much higher, let's say by multiplicative factor 1 plus tau, where tau is some parameter, than what the actual conditional variance is, then you just drop that vertex. Okay? And again, you have to work with estimates for what these conditional variances are and not the actual variances. All right, so that's the algorithm. And now let's look at what the algorithms do, what our algorithm and what existing algorithms do for a simple toy model, right? And we also have some experiments on real world data sets, but let's look at a simple example to illustrate the difficulties and challenges in learning GGMs that have long range correlations, such as simple path, which violate the well-conditioned assumptions used in previous works. So the example is very simple. It's just the path or the random walk model as before, plus some cliques. So the dependency graph has this very simple structure. It's just a single path on P over 2 vertices. And then you have this isolated 4x4 cliques, which are kind of just doing their own thing independently. That's the dependency graph. The maximum degree of the graph is 3. And because of the long path, it becomes ill-conditioned under the various notions of let's say Glasso or climb, so their bounds do not apply. And here's what the precision matrix actually looks like pictorially. So most of the matrix is 0, and then you have like this 4x4 blocks which are non-zero along the diagonal, and then you have this tri-diagonal matrix corresponding to the simple path. And imagine there being a parameter rho which controls the intensity of what's happening on these 4x4 cliques. All right, so now we ran some simple experiments on implementing Glasso and climb and our greedy algorithm, and this is what happens. So if you see from this simple animation, greedy kind of quickly converges to the true graph, whereas others are taking longer. And here's what the final recovered graphs are for the simple model. You can see again that greedy kind of recovers the original graph with much better accuracy. And this also bears out in plots where if you look at the paper, there'll be more details. But essentially, the greedy prune algorithm has the best error for a given sample complexity and as the dimension grows. In terms of the L1 error in recovering the precision matrix, that's number one. And in the context of learning the graph, I won't talk about these things too much. In the context of learning the graph, once again, we try to quantify how many samples do you need as a function of the dimension to recover the underlying graph. And here, for a recovery just meant that you had to get certain accuracy in the edges and we kind of did the best possible choice of the hyperparameters and so on. So for the simple challenge, where the intensity on the cliques was 0.95, you can see the greedy prune is pretty flat. The sample complexity is not growing too much. Whereas for climb and A-climb, the sample complexity is kind of almost growing nearly linearly with the dimension. So that's the number of samples you need for the algorithm to empirically learn the structure, the dependency graph. So not just the theoretical ones, right? So if you go back here, it seems like, maybe Glasso is doing very well, and maybe it's just a shortcoming of the analysis. But if you tweak the intensity on the 4x4 cliques, you start seeing that Glasso now starts growing linearly with the dimension, whereas greedy prune still remains flat. And there's one algorithm, the Menhausen MB algorithm that I haven't specified before. It seems to be doing well, but now if you change the intensity again, that starts growing linearly, whereas greedy prune stays flat. So in summary, for the simple challenge, greedy prune, where various values of the intensity stays nearly flat and has logarithmic sample complexity, whereas the other methods you start seeing that they need linear sample complexity to recover the underlying graph. So here's a quick summary of what I said so far. We have the greedy prune algorithm, which learns attractive models with d log pure kappa square dependence in sample complex and quadratic runtime. And similarly, d squared log pure kappa to the 6 sample complexity for Walk-Summable models. There's some additional properties. As I said, it recovers the guarantees of Glasso and Klein. And you can also use it for non-Gaussian distributions if you're interested in learning the precision matrix. But let me not get into that for now. So now that I've stated the results and what the algorithm is, let me say a few words about the analysis and what goes into it. So here's a quick summary again. The main results, the main parameters are you have the degree d, which is the maximum number of edges that any vertex is adjacent to, the dimension p, the number of samples, and the pairwise correlation kappa. So let's look at what happens for attractive models. And the analysis for attractive models is actually pretty simple. And the punchline is that the conditional variance function is supermodular for attractive models. So more concretely, let's fix a vertex 1, and let's define a function on the subsets of other vertices, which is f of s is the conditional variance of x1 given the variables in S. And there are these earlier works from 2006 and 2012, really nice papers, which showed that if your model is attractive, then the function, the conditional variance function, is monotonically decreasing and is supermodular. And the supermodularity essentially says that if S and T are two subsets where S is contained in T, then the decrease in conditional variance that you get from adding a vertex is higher for the smaller set S as opposed to T. And this is the same property that showed up in Ankur's talk. And it's useful for us for the exact same reason. So why is supermodularity useful? Well, once you know it's supermodular, optimizing supermodular functions, you can use a greedy algorithm, and it will find the minimizer. So almost says that basically you're done. You just have to apply the greedy algorithm on conditional variance function. It will work because your function is supermodular. There are some technical catches that you have to work through with some care. They're not exactly trivial, but you have to use some non-trivial estimates on OLS. The two main complications are that you don't have access to the exact estimates of the exact values for the conditional variance. You only have estimates, and you have to be very careful on how accurate you are because we're shooting for this 1/kappa squared style dependence. And finally, you need to also prove that if you miss a vertex, then you're noticeably away from the optimum. It's kind of some sort of stability result saying that the optimum set is almost unique in a robust way. So that's all I want to say about recurring attractive Gaussian graphical models. Let me now say a few words about what happens for Walk-Summable models. Well, the algorithm for Walk-Summable models, as I said, is exactly the same. It's just, again, the greedy algorithm on the conditional variance function or estimates of the conditional variance function. But the main difficulty now is that the conditional variance function is no longer supermodular. And in fact, there are various notions of relaxed notions of submodularity or supermodularity in literature. And the conditional variance function for Walk-Summable models doesn't satisfy any of them. So why does the greedy algorithm still work? And why would you hope that greedy still works? And here we kind of draw inspiration from literature on Laplacian graphs and in computer science. So the first thing we use is that Walk-Summable models are actually equivalent to something called symmetric diagonally dominant matrices that I'll define precisely in a second. And if your precision matrix has this seemingly stronger property of being SDD, then you can show that neighbors have significant effect on conditional variance. I'll make this precise in a second. So what is a symmetric diagonally dominant matrix? Theta, any semi-definite matrix, is SDD. If for all I, the corresponding diagonal entry, theta II, is larger, or at least as large, as sum of absolute values of all the other entries in the row or column. So theta I must be larger than sum of absolute values of theta ij for j is not equal to I. And there's this sort of folklore, but also explicitly stated result from 2009 saying that if a matrix is walk-summable, if and only if there is a diagonal scaling D of non-negative entry such that the matrix D theta D is symmetric diagonally dominant. It sounds like, okay, just some algebraic property. Why is it useful for us? Well, one nice property of the greedy algorithm is that it's kind of invariant to diagonal scalings. So if the algorithm works when I scale up each of the variables by some numbers, then it'll also work for the original distribution that you started out with. So to show that greedy works, you just have to show that maybe there's some potentially nice scaling of your variables for which greedy works. And this means that it suffices to show that greedy works for SDD matrices. So if you show that greedy algorithm works for SDD matrices, then it'll also work for walk-summable matrices. Okay. So let me now say why you expect it to work for SDD matrices. So for intuition, let's assume that you normalize the precision matrix so that it's not only SDD, but also satisfies this additional condition that all the diagonal entries are 1. Okay? And in the actual analysis, you don't need it. This would be a very strong normalization. But for intuition, let's assume that you have an SDD matrix where all the diagonal entries are actually 1 in magnitude. Now, what does a pairwise correlation condition imply for us? If I tell you that the parameter kappa of theta is at least kappa, then it has a nice meaning in terms of what the matrix looks like. It says that every non-zero entry in your precision matrix has magnitude at least kappa. Okay? So you can't have very tiny entries in your matrix anymore. And what we show is that if your matrix is SDD and satisfies this normalization, then the conditional variances are actually bounded. In particular, if I have two vertices, I and j, which are adjacent, then the conditional variance of xi, given any neighbor of xi, let's say xj, is at most 1 over kappa. And here, remember that we're thinking of kappa as a fixed number that doesn't scale with the dimension p. Right? So it's kind of very interesting because we're saying the conditional variance is independent of the dimension p for any SDD matrix. If you go back to our running example of the random walk matrix, remember that the variances of the original model can grow linearly with the dimension p. Variance of xi plus 1, which was some of the prefixes, is actually I plus 1. And I is going from 1 through p. So it's linear, can be as high as linear in p. Whereas the conditional variance for any edge is actually just 1. Right? So there's this big gap between what the conditional variance is and what the actual variances are. And this property is actually not true for general sparse precision matrices. To see such a decrease in the conditional variance for general sparse precision matrices, you have to actually add all the vertices and not just a single vertex. Okay, and this is kind of what makes the analysis go through. And at a very high level, why this helps is that, remember at the beginning I said, even the earlier works, they worked if you knew that the conditional, if the variances were bounded, right? But now we're exactly showing that. If I recover one neighbor and a condition on it, the model that I have has all variances bounded. So in particular, it becomes well conditioned in the usual sense, and you might as well have used the existing algorithms. But here you can actually give a simple analysis to show that the greedy algorithm also works once you have these conditions. Okay. So that's at a high level. So the main ingredient is this bounded conditional variance condition, which is true for SDD matrices, and is not true for general sparse precision matrices. And in fact, this is not true even for walk-summable matrices if you don't normalize it appropriately. Right? So you have to first do this kind of conversion to SDD matrices to find the right version of the statement even. Okay. And the proof of this inequality uses something simple from the Laplacian graph literature, which is just the triangular inequality of effective resistance metric on graphs. So again, I don't have time to go in depth about what these quantities are. But basically, conditional variances on an SDD matrix correspond to certain kinds of effective resistances. And then you can connect it to triangular inequality to prove this conditional variance bound. Okay. So that's all I wanted to say. Let me now summarize the three parts. So in summary, the main question that we started out with is whether we can learn the structure of sparse GGMs with sample complexity that is polylogarithmic in P and fixed polynomial runtime for fixed degree D and pairwise correlation kappa. And you want runtime that is P to the little o of D. And what we saw is that this is a very well studied problem. It's practically important. And there's a simple greedy algorithm which kind of recovers previous guarantees and solves very interesting special classes of models. But there's a lot more work to do than, there are actually many interesting questions here. Obviously, the main one is whether we can find richer classes of models where you can achieve similar efficient recovery guarantees with small sample complexity. And there are also related questions that are still unknown. For example, what if you have sample access to a GGM? And I also give you a candidate graph, and maybe let's say even a precision matrix. Can you check if this is actually the right model? Can you test if this is the right model with sample complexity without maybe testing is easier than learning? And just as an Ankur stock, what happens if you have hidden variables in your GGM? There is some work, some really nice work due to Chandrasekharan and others on learning GGMs with hidden variables. But can you combine that sort of line of work with the new information-theoretic bounds that we are seeing? And finally, are there fundamental bottlenecks to trying to get the speed to the little o of D runtime for general Gaussian graphical models without any of the underlying assumptions that we are making here? And in fact, we can actually show that the greedy algorithm that we have also breaks for general GGMs. And my conjecture, I actually think the problem is hard now, having thought about it for a while. And my guess is that there is no P to the little o of D algorithm for learning general GGMs with sample complexity that is, even maybe polynomial in D, 1 over kappa, and log P. But we have no clue as to where the hardness could come from, how to show such a condition, or even what possible hard instances could look like. So all of these are really fascinating open questions. And that's all I had to say today.
Thanks for a great talk. Any questions for Agu? If you have one, please unmute yourself and feel free to ask. And maybe to start, let me. I had a question, and I think it is the one that you pointed in the middle of your talk, and you decided to skip over. which was, is there any hope to generalize this greedy type of algorithms to more general classes of continuous graphical models beyond Gaussian? So if I have, like, similar to Ancours or Markstock today, if I have a graphical model on continuous variables, but which includes like multi-body interactions in the entry function.
That's actually interesting. So maybe, but I'm not sure. What I had in mind was something simpler. I think basically saying, suppose I don't know my underlying distribution, my continuous distribution is Gaussian, but I, for some reason, know that the precision matrix is sparse. So then I can still use this algorithm to learn the precision matrix.
So precision matrix is defined as inverse of the covariance.
Right, that's
general.
all.
Okay.
Yeah.
Okay.
Yeah. Inverse of the covariance, and as long as you have like exponential or sub-exponential tails, basically matrix convergence bounds on how many samples you need to estimate the covariance matrix, the bounds would go through even if you don't assume the matrix is distribution is Gaussian. So it's kind of a different orthogonal axis.
Yes.
But then it's not clear how you can interpret the precision matrix if your distribution is not Gaussian. But apparently some people in, when I talked to some people who work in bioinformatics, that was one of the first questions they asked is, okay, precision matrix is meaningful for us, but we don't think our distributions are Gaussian. And the works actually, most of the algorithms that work for GGMs also work in this more general setting. And the question that you asked is kind of wide open even for continuous things, I think. Finding interesting conditions when you can achieve such guarantees is quite open.
Okay, thank you.
Sure.
Are there any other questions?
Well, if I may, it's Mark speaking. I have one.
Go ahead.
Yeah. So here you mentioned, for instance, in your conjecture, you don't believe that there is a polynomial time algorithm for that scale with D log P samples, right?
Mm-hmm.
The recovery structure with D log P samples.
Right.
What if I gave up on high dimensionality? I'm okay to pay a price P log P. What will be your take on? So I still have a D-sparse matrix, let's say, but I have P log P samples. Do you think it's still independent of the condition number? Or do you think we can find a polynomial time algorithm that is independent of the condition number in this case?
So you're saying the sample complexity is P of P?
Yeah, it's basically you trade off. Do you believe that we can trade off computational complexity for sample complexity?
Right, but you still have to assume the pairwise correlation condition, right?
Sure, yeah.
Yeah, so in that case, maybe it might be possible. Like, let's say you try to estimate the covariance with very good error, which would also give you very good error on the precision matrix.
The reason I'm asking is because every time we would like to do, well, we studied also parameter estimation, this problem, and it's, I mean, what we believed, me, Silan, and Andre, is that for parameter estimation, you really have to have a dependency in the condition number somewhere. But when it comes to structure, it magically disappears. So if you want to learn it's not clear that if you have more samples, you can still get away with an independent condition number. Because if you try to reconstruct the covariant matrix, you may have an error that is potentially big because of that. Right?
Right. Yeah, that makes sense. I mean, if I want to get an epsilon approximation to the covariance matrix, you need roughly O of P over epsilon square sample.
Exactly, yeah.
And this is in the Laplacian order. Right, so, and that's kind of tight for general Gaussian. So what you said might be true if you want to do parameter estimation.
Yeah. So I don't know if you had considered this or not.
No. I mean, that makes sense. On the other hand, I mean, if you learn the dependency graph, then it becomes a D by D problem.
Yeah.
Right, and then maybe you still have some dependence on the condition number, but on this D by D submatrix.
On the reduced one, yeah.
Right, yeah. Yeah, it seems like you need some dependence there.
Yeah.
Excellent. I think we can move to the discussion session to continue discussion. But before that, I wanted to thank all the co-organizers of the workshop, and in particular, so Jeff, Matthew, and Andrea for putting up the program. And most importantly, I wanted to thank all the IMA staff, so Catherine and Georgia and Daniel, who really made an excellent job and allowed this workshop to happen. So thank you very much.
Thank you.
Thank you, Andre, and thank you,